Okay, so we're gonna, like we said, we're gonna finish. Oh boy. We're gonna finish the infinite line charge and then we move to some examples. Okay. You remember how we did the same problem earlier? Yes, you guys are not back yet?
Which problem, sir? With the wall, you mean?
The infinite line charge.
That's the one where you said it was at a wall or something.
No, man. Last week. This is what we did last week. Let me find it. You guys not doing enough work now. You remember this problem? The electric field of an infinite line charge. We did this. And we went through all of this. All of that. And get electric field to be equal to this. Now I'm gonna show you how much simpler it is with the using Gauss's law. Here's the same problem. But using Gauss' law, the first thing you do, you make a Gaussian surface. So here is your Gaussian surface is a cylinder. Or the simplest one to choose is the cylinder. So Gauss law states that Q is equal to the integral around the closed surface of d dot ds. Your ds for the cylinder, your surface for the cylinder is around the side, the top, and the bottom. Okay. Your d is radial outward from the charge. So this is your d. So So your D is in the R direction. So it's D, dr, AR. Because there is no component going out any other way. Your surface is as follows. The side is R d phi dz in the AR direction. You understand how you get that?
So it looks like a position vector and your
Okay. This surface is in the AR direction. The AR is the direction that is normal to the surface. So DSAR, right? And DS is the differential angle D phi times DZ. In other words, the surface area of the side of a cylinder is 2 pi r times h. So r d phi is that differential circumference, and dz is the differential height. There's r d phi dz ar, which when you dot ds with d, this goes away. AR dot AR is 1. So you end up with dr r d phi dz. So,
sir.
yes, go ahead.
Yeah, could you go over the differential surface here once more?
Differentials.
When you're finding R d phi dz, if for the cylinder,
Right here.
yes.
Okay. Or here. Okay. There, what's the area of the side of a cylinder?
The side, sir.
Yeah.
I mean the circumference.
The area of that circumference.
Should be two pi r.
Times h.
Yeah, and then
Right? So if you want a piece of the side, the area for a piece of the side would be the fraction of 2 pi because around the entire circumference is 2 pi. For, say, 90 degrees, it would be a quarter of 2 pi, or 2 pi over 4. So the d phi would be 2 pi over 4. Because all this is, all this is, right? For the complete, for the entire side, it would be r times 2 pi times whatever z is. 2 pi r times height. Your height is z. But it's just written this way. So if you are just dealing with a quarter of the cheese, of the tin of cheese, that's your d phi. And if you are not dealing with the entire z, it would be dz, the differential length. Right? So for your side, this would be your formula. Now, so this is your dz, ds, this is your d. D dot ds is this dot this. Right? So AR dot AR gives you 1. So you're left with dr, r, d phi, dz. Follow me?
Yes, sir. Kind of find the product, and that's the cross product is the dot product of two vectors, similar vectors equal.
All right. So no. So this is your differential E or your differential D. So for the entire cylinder, you will simply integrate going around the cylinder and to the height. So 0 to 2 pi and 0 to L, whatever L is. For the top and the bottom, right? That would be 0. Why? Because D is only radial. D doesn't go up or down. So you just put that to 0. When you do this integration, you simply get this. Which is the same thing as you got above when you did all those integration and whatever. So using Gauss law is much simpler.
So is it that you can use it for any shape too?
For what?
Any shape. Indicate does it only apply to infinite line charges?
No, man, any charge. Any charge. Let me see if we, okay. When we do the examples now, sorry, we will do some that are not. Okay. This. So I didn't have it on my desktop. It does. All right. So you owe me a problem. Which one did I assign you? Can someone tell me which problem you were supposed to do for your homework? I guess no one did it, right?
On the first class, sir.
Huh?
No, since it's my first class.
So it's your first class?
Yes, sir.
Don't blame me. We have, I think, 24 people in this class. Right. At this moment, we have 16 people. Can anyone even tell me the problem that I assign you? Last class.
Hello, sorry, you hear me?
Yeah.
Okay. The problem, well, I didn't write out the initial statement. I only jot down the initial value of Q and Y, but I wrote down what the questions were. The other questions were, it was a charge equals to 8 nanocoulombs exists somewhere along along the y-axis where must Q be for the total electric field to be zero at the origin. That was one of the questions.
That was the last one.
Yes, it was the first question out of the two in that question that you gave.
Oh,
I
sir.
think it's the question above this one, sir. Yes, sir, this is the question.
Okay. So somebody walk me through it now. Or let's do this. You were supposed to have done this for your homework. Who at least attempted the homework? Should I call on people?
Sir, I can try to start it, sir. I wrote it down, but it was on some sheets of paper. So first thing you would be to, we have the information, so you consider the equation to determine the electric field intensity.
So the electric field intensity would be that which is due to the line charge plus that which is due to the point charge, right?
Yes.
So E equal EL plus EQ, where EQ is that due to the point. EL is rho L over 2 pi epsilon naught rho. A rho. EQ is Q over 4 pi epsilon naught y square minus AY. So this is your line charge. This is your point charge. Hmm? So E due to this is this. No, E due to the line is given above. E due to Q is this expression, right? So now you solve for Y. You get 2 meters. So you locate Q at 2 meters on the Y-axis for your field here to be 0. So Q over 4 pi epsilon naught R squared equal 18. And you solve for Q.
Chair, could you rewrite that question, please?
The question that we just finished,
Yes, sir.
Y
Don't fully understand what you did in the letter N.
did you attempt it?
No, sir.
Well, I can't go over that. Uh, Okay. So attempt this one, problem 225. If you just sit there and don't attempt, and when you get homework, you don't do it, what you gonna expect? So I'll give you 15 minutes to attempt 225. The volume of a cylinder is 2 pi r.
Square times the height.
Right.
Sir, could you possibly scroll back up to the question to get it in the recording?
It was in the recording before we break it up.
All right.
It would be a it would be a shame if you get something like this to do in an exam and you can't do it. And the only way you're gonna be able to do this is if you practice. Okay. Attempt 229.
Sir,
Yes, I'm here now.
sir, where it says rho is greater than or equal to 2, less than or equal to 4, should that be R?
Rho.
Yes, sir.
Okay. Yes, at least you're paying attention. In cylindrical for the radius in cylindrical coordinate system, some books use R, others use rho. I should have pointed that out. So the answer to you is yes. Anyone with a reasonable attempt? Okay, just let me know when you're ready.
Sir, got the equation for Q.
Okay,
So,
what is it?
so D times integral between 2 and 4 R. Integral between pi by 2 to pi d phi. Integral between 0 to 4 dz.
Integral?
So D,
Hmm.
yeah, I use the two row A row plus sine phi is it?
Hmm.
Yeah. Multiply by integral between 2 to 4 of R. But or row since in the book it
Yeah.
says row. Yeah. And then
So, so
pi by 2.
this
Yes,
is what you got.
yes, sir. I didn't evaluate it. I was just checking if the equation is correct.
Okay.
Did I get that?
Yes. So here it is. Anyone else attempted? I guess not. So you are trying, Mr. Thompson. I'll work with you. So see if you get the 6. Cool on. So as soon as you get that 6, you can go ahead and attempt 230.
Sir,
Yes.
what happens to the 2-row A row? No, the unit vector A for row. When I find the unit vector for Z and it was 1, so it came out the equation. But then,
Come again.
all right. So given that the Z value was 4 and
Mm.
try to find the unit vector for Z, it was 4 over square root of 4 squared, which was 1. So I just multiplied the rest of the equation by the 1. But now I have D equal to 2 row unit vector for row plus sine phi is
I don't understand.
the trying to find a row.
Arrow. Why?
So sorry, in order to complete the equation, I think I would need it. Right? Or why not?
No man, you don't need it. Look at it. You know that this, the correct angle is a type, right? It's supposed to be that. So this is your DS. Your DS is two. You go you go from what the question is. Find the electric flux passing through the surface defined by this. All right? So let's do a little thing. So you have all right? So this is your cylinder. So then your row is from here to here. All right? So it says the surface defined by row from 2 to 4. So say you'd have to say this is 2 here, And this is 4. All right? So it's defined by that row and your theta or your phi would be this cutoff trees here. So this would be your phi. And your Z would be that. Okay, I know something. I remember I remember we see a nice plot, a nice diagram here. That is what I'm trying to draw, but obviously, there you go. It's exactly like this. So 2 to 4, and this would be your angle here, your phi, and this would be your Z. So if we go back to our problem now, so this, so you picture the 2 to 4. Right? And the angle, and the Z. So the 2 to 4 would be rho d rho. Get it now? Am I on mute?
Oh, yes, sir.
You get it?
Yes, sir. If I were to distribute the sine phi AZ to the integral between pi by 2 and pi, then I would get, yes, sir. I think I would get it.
Mhm. Look now, when you do this is your D, and this is your DS. Right? So when you dot this and this, it disappear. Now this with this is equal to 1. When you dot this, A rho with AZ is 0.
Is that one of the dot product rules?
But me give. Okay.
Sure.
Yes.
For cos phi a theta, is trying to get the why they use phi and theta, or are they the same unit?
No, 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 no. No.
Right.
Remember now, this is spherical coordinate now. So the units for spherical coordinate would be R or rho. In this case, I think it's R. R and theta when you go around, and phi when you come down along the surface. Remember when we demonstrate using the orange, coming from the center to the surface is R, going from the North Pole down to the South Pole, that's phi, and going from east around is theta. So no, they are not the same. So in spherical coordinate, you have a AR, a theta, and a phi.
Oh, so phi would replace what we would call z for the cylinder.
Okay. Okay, but just think of them as different, two different.
Oh, yes.
Anything yet? Anybody get anything?
Sir, I wrote down to integrating minus cos theta a theta r.
All right. So you get the flux density, you get the function for the flux density of the sphere, right?
Wait, I got
No, you get this is given the function, right? So this is pretty much similar to the one above, except we are dealing with spherical coordinates. You with me?
oh yes, sir.
So you are dealing, so all right, how we put it now? So instead of having Z as a cylinder, you have it like this. And then something, you know what that means?
Yes, sir.
So your DS, right?
I think the problem I was having, sir, is picturing the surface, the differential surface.
Oh,
Yes.
okay. So record that and look it over. So, I mean, the thing is that using the Gauss law, the problems become so, oh, there we go.
Oh, yes, sir. I got that last one. Minus cos theta.
Mhm. Oops, sorry. This.
Yes, sir.
And then you just plug in the limits and you work it.
What was missing from mine was because I used the differential surface from the cylinder, so I wasn't picturing that should be
Oh, okay. You have to kind of separate them in your mind, a sphere and a cylinder.
this.
All right. Okay. Do do part A of this one.
So if I was going to try to use Q equals 2 pi r br times L, but um
2 pi r what?
times it would be L would be
Your height, right?
the height. But it says per meter length of shell. I'm not sure what to consider as. I was going to use 1 meters.
Alright.
Yes, yes, sir.
So we have this, right? Which we have been using all along. Now, I guess what this problem is want to bring out to you, right, is that it's a shell, right? And the charge is on the shell. It's not like the wire, right? It's a shell. This is just a shell. So anywhere between the axis and the inner surface of the shell, there is no charge enclosed. Right? So based on Gauss's law, if there is no charge enclosed, there is no electric flux. Or d dot ds is equal to 0. On the outside of the shell now, where the charge is the charge of the cylinder, the charge enclosed is this. So the inside of the hollow shell there is no charge enclosed because the charge is on the cylinder, which is hollow. The application of this is like with coaxial cable or with magnetic shielding and things like that. So instead of having a wire with a charge, right? Instead of having a wire with a charge, you would have the inside of the shell, the charge is 0.
So it's hollow inside. So.
Yeah, it's a shell.
Oh, all right.
Right? So this is how they you know this is how they do your magnetic shielding, so that radiation don't kill you. Right? So if you're asked to let me see, a good example now would be you see, like when you do your x-rays, right? There's a a magnetic shielding for the rays. So standing outside, nothing can happen to you. All right.
Oh, yes, sir.
So let me give you one more for which I want you to tackle at home. So number 235. So try that one for class next week.
Yes, sir.
And I hope you know I can call on somebody except you, Mr. Thompson, and they can answer. As a matter of fact, let me quickly let me say who I'm going to call on. Mr. Swires. All right. So do that one for next week. Okay?
Yes, sir. Sir,
Yes.
I recall I said that for the final exam, we were going to do the test on campus.
Right.
Was there supposed to be a test before?
Yes, you're gonna have a midterm, which I was planning on giving you a very easy midterm, but since you guys not doing any work, I probably have to put that one on campus too and give you something to wake you up. Next week, I'll tell you when that will be. All right.
Sir.